Hello, in today's video we're going to be talking about calorimetry. Now this is one of those classic general chemistry problems that every general chemist in the world who's gone through chemistry knows how to solve and deal with. So what's our setup? What are we doing? In the previous video we came up with an equation that related heat to the mass of a substance times the specific heat capacity of that substance times the change in temperature. So we have an equation. Q is equal to mc delta T. Remember, the Q is the heat, m is mass, C is specific heat capacity, and delta T is the change in temperature. This is going to be in Kelvin if your specific heat capacity table is given in Kelvin. Okay. So what do we know about this? Well, let's say we have two different substances. I'm not very good at drawing, but this is my depiction of what a calorimetry experiment is. Over here we have a piece of metal. This is supposed to be a cube of metal. From this cube of metal, we would be able to identify what the heat is of that metal, how much heat was lost or gained by it, if we knew the mass of the metal, the specific heat capacity of the metal, and the change in temperature of that metal. Okay. Over here, let's say we have a styrofoam cup. That's the cylinder. We have this tube. That's supposed to be a thermometer. And then we have a certain mass of water over here. So the three pieces of information we can get about this metal is we can get the mass of the metal, we can get the specific heat capacity of the metal. The way we can do that is if we know what metal it is, let's say aluminum or copper or silver, we can look up the specific heat capacity in a table, and we can use that as our C. And let's say that we've heated up this piece of metal. I'm going to use a Bunsen burner. I'm heating this up to a certain temperature, so I know the initial temperature of the metal. I know the exact same things over here for the water. I've measured the mass of the water. I've measured the specific heat capacity of the water. I haven't measured it, I've looked it up in a table. You're going to eventually do enough of these problems where you're going to commit the specific heat capacity of water to memory, but it's okay if you don't remember it right now. And we have a thermometer in here, which allows us to figure out what the initial temperature is of the water. Great. So we have all of this information. Now, this is something that you're going to do in laboratory. You have these three pieces of information. Now, let's say I took this hot piece of metal and I put it into this styrofoam container that contained a certain mass of water. What do you think is going to happen to the temperature of the water? I'll give you a few seconds to think about that. So you're taking a hot thing, you're putting it into a cooler amount of water. Okay. Well, what you should come to realize is the hot thing, the metal, is actually going to reduce its temperature. It's going to lower its temperature because hot things, when they come in contact with colder things, give up its heat to that colder thing. The colder water is going to actually increase its temperature. Okay, that's cool. But if over time we let this metal sit in there for long enough, what do you think the temperature final of the water is going to be? And what do you think the temperature final of the metal is going to be? So we knew that the initial temperature of the metal was bigger. The initial temperature of metal is greater than the initial temperature of the water. But after we placed this metal into the water and we waited for a few minutes, what's going to end up happening is the final temperature of the metal is going to exactly equal the final temperature of the water. It has to. This is why your ice melts in your glass in summer. The water, if you have ice water, your water is at a certain temperature. It's hotter than the ice. The liquid water melts the ice and tries to give it, they come to equilibrium. So they want to be at the same temperature. Same thing is happening here, although we're not melting anything. So the hot piece of metal is lowering its temperature. The cold water is raising its temperature. And the final temperature final of the metal, is going to be identical to the temperature final of the water. We're going to let this metal sit in here for long enough that it's going to eventually come to equilibrium. Great. That's really nice. We now know a piece of information. This makes us have one less variable. Okay. You might be saying to yourself, why does it make us have one less variable? Well, what else do we know about the heat? So we know that the heat of the metal, we can figure it out. If we were to measure the temperature final of the metal, the initial temperature of the metal, specific heat capacity of the metal, and the mass of the metal, we can calculate Qm. Great. We can do the same thing for QH2O. Now, as it happens, the amount of heat that is released, that is given off by this hot metal to the water, is exactly equal to, but opposite in sign, to the amount of heat gained by the water. Whatever heat was given off by the metal is now given to the water. The water absorbs it and raises its temperature. So we can actually set our Q's. Q metal is equal to the QH2O with one very big difference. The sign has changed. That's it. However much heat was given off by this metal was gained by that water. So there has to be an equal but opposite sign. Okay. So what's a cool process of this? Now I'm going to leave this up to you. We have Q of metal. This is going to be the mass of the metal. I know it's a lot of derivations, but this is the beauty behind calorimetry. The mass of the metal, specific heat capacity of the metal, temperature final of the metal, but that's just equal to temperature final of the H2O. So I'm just going to call that temperature final minus the temperature initial of the metal. It's going to be equal to minus the mass of the water times the specific heat capacity of the water times temperature final. Those are going to be equal to each other. This temperature final and this temperature final are equal, minus the temperature initial of the H2O. So this is our big conclusion. All of me talking today, talking about the heat equation, these three different variables, adding in the fourth variable of the temperature final. We don't even know what it is, but we know that they're equal to each other for the metal and the water. We know that the amount of heat given off by the metal is gained by the water, so it has to be equal but opposite signs. We can plug in our values for our Q's, which come from this equation, and we come up with something that looks like this. Now, I don't want to go through any more derivations. However, I'm warning you right now, tomorrow in class, I'm going to ask you to calculate the temperature final for a system given at equilibrium. I will give you the mass, the specific heat capacity, the initial temperature of the metal, the mass of the water, specific heat capacity of water, and the initial temperature of the water. And you have to solve this using algebra and get temperature final by itself. So I'm going to leave that for you to work on tonight. This is what we do in calorimetry. Generally what's going to happen is you're going to be given all of the variables except for one. So you're going to figure out what the last variable is by solving this problem with algebra. This is our equation that we're going to be using quite often for the rest of rest of the week, rest of chapter 6. So calorimetry is a big important part. I guarantee you will have one of these on your final as well as on the next exam. So with that, I want to leave that to you. I hope you all work on this tonight so you can come in and we can get some good work done tomorrow. I'll see you all tomorrow in class.